preparing for a Graduate Engineer Trainee (GET) at Skyroot Aerospace interview. You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. Tell me about yourself and why you want to join Skyroot Aerospace as a Graduate Engineer Trainee. I would start with my engineering background, core strengths, and one project that proves hands-on problem solving. Then I would connect it to Skyroot, private space, fast development cycles, and launch vehicle systems where fundamentals matter. For example, if I worked on propulsion or structures, I would highlight design, testing, failure analysis, and teamwork. The key is to show curiosity, ownership, and readiness to learn quickly in a high-accountability aerospace environment. While answering, focus on your engineering foundation, hands-on projects, interest in rockets or space systems, and why Skyroot's private launch vehicle mission fits your career goals. Question 2. What do you know about Skyroot Aerospace and its Vikram launch vehicle program? Skyroot Aerospace is an Indian private space launch company building Vikram launch vehicles for small satellite missions. I would mention Vikram S, which demonstrated suborbital capability and proved the company's execution strength. Skyroot's approach seems focused on modular designs, faster development, and cost-effective access to space. For a GET role, that means exposure to real launch hardware, propulsion, structures, avionics, manufacturing, testing, and cross-functional engineering from an early stage. Make sure to cover Skyroot's role in India's private space sector, Vikram launch vehicle family, small satellite launch focus, Vikram S milestone, and collaboration with India's space ecosystem. Question 3. Can you explain the rocket equation and why it matters in launch vehicle design? The rocket equation links velocity gain to exhaust velocity and the ratio of initial mass to final mass. In simple terms, more efficient propulsion and lower dry mass allow higher delta V. This is critical because launch vehicles must overcome gravity, drag, and reach orbital speed. A small reduction in structural mass or improvement in specific impulse can meaningfully increase payload. That is why propulsion, materials, staging, and mass optimization are tightly connected. In your answer, talk about delta V, exhaust velocity, mass ratio, propellant fraction, staging, and why reducing structural mass significantly improves payload capability. Question 4. What is the difference between solid, liquid, and cryogenic propulsion systems? Solid propulsion is simpler and reliable because fuel and oxidizer are cast together, but throttling or shutdown is difficult. Liquid propulsion uses separate fuel and oxidizer, so it offers better control, restart capability, and mixture management, but needs pumps, valves, and feed systems. Cryogenic propulsion uses very cold propellants like liquid oxygen and liquid hydrogen or methane, giving high performance but adding thermal and handling complexity. Selection depends on mission, cost, thrust, and reliability. Be sure to mention propellant state, controllability, complexity, storage, specific impulse, thrust response, reliability, and typical use cases across launch vehicle stages. Question 5. How would you approach the structural design of a launch vehicle component? I would first identify load cases, axial compression, bending, vibration, acoustic loads, pressure, and thermal effects. Then I would choose materials based on strength-to-weight ratio, manufacturability, and compatibility with the environment. After initial sizing, I would run analytical checks and finite element analysis for stress, deflection, buckling, and modal behavior. The design should meet margins without becoming overweight. Finally, I would validate it through inspection, qualification testing, and correlation with analysis. While answering, focus on load cases, material selection, stiffness, buckling, vibration, thermal effects, manufacturability, weight optimization, factor of safety, and validation through analysis and testing. Question 6. What do factor of safety and margin of safety mean in aerospace design? Factor of safety is the ratio between failure load and expected design load, while margin of safety tells whether a component has adequate strength against a defined requirement. A positive margin means the design passes. A negative margin means it needs redesign or better justification. In aerospace, we cannot simply oversize everything because mass is expensive. So the goal is controlled conservatism, supported by analysis, material allowables, testing, and clear documentation. Make sure to cover design allowables, limit load, ultimate load, uncertainty, test validation, positive versus negative margin, and why aerospace avoids excessive conservatism. Question 7. How would you handle thermal challenges in a rocket engine or launch vehicle subsystem? Thermal management starts with identifying heat sources and paths: conduction, convection, and radiation. In propulsion, combustion temperatures can exceed material limits, so solutions may include regenerative cooling, ablative liners, insulation, or high-temperature alloys and composites. I would also consider thermal expansion, seal behavior, and cyclic heating during tests. The design must be checked analytically and then validated with thermocouples, hot fire data, and post-test inspection. In your answer, talk about heat transfer modes, combustion temperatures, insulation, regenerative cooling, ablative materials, thermal expansion, material limits, and thermal testing. Question 8. Explain the basic role of guidance, navigation, and control in a launch vehicle. Guidance decides where the vehicle should go. Navigation estimates where it actually is, and control generates commands to keep it on track. Sensors like IMUs, GPS, and pressure or rate sensors feed data into estimation algorithms. Control outputs may drive thrust vector control, reaction control, or aerodynamic surfaces depending on vehicle phase. The challenge is maintaining stability despite wind, mass changes, vibrations, and engine disturbances, especially during high dynamic flight. Be sure to mention trajectory planning, sensor inputs, state estimation, control commands, actuators, stability, disturbance rejection, and coordination between software and hardware teams. Question 9. Why is staging used in rockets, and what are the engineering trade-offs? Staging improves performance because the vehicle discards empty tanks, casing, engines, and structures that no longer contribute to acceleration. This improves mass ratio and helps achieve orbital velocity. But staging adds complexity: separation mechanisms, avionics sequencing, structural interfaces, ignition reliability, and safety clearances must work perfectly. A failed stage separation can end the mission. So staging is a performance necessity, but it must be engineered with high reliability and rigorous testing. While answering, focus on discarding dead mass, improving delta V, staging events, separation reliability, structural interfaces, ignition timing, complexity, and mission risk. Question 10. What is thrust-to-weight ratio, and why is it important during launch? Thrust-to-weight ratio compares engine thrust with the vehicle's weight. At liftoff, it must be greater than 1. Otherwise, the rocket cannot rise. A higher ratio reduces gravity losses and improves early acceleration, but too high a ratio can increase structural loads and vibration. Too low a ratio wastes propellant fighting gravity. For launch vehicle design, it affects engine sizing, trajectory, payload capability, and structural requirements. Make sure to cover thrust, vehicle weight, liftoff condition, gravity losses, acceleration profile, payload constraints, and why too high or too low thrust creates design issues. Question 11. What manufacturing methods are relevant for modern launch vehicle development? Modern launch vehicles use a mix of manufacturing methods. Composite winding or layup is common for lightweight structures and motor casings. CNC machining is used for precision metallic parts. Additive manufacturing helps create complex engine components with internal channels or reduced part count. Welding, bonding, and casting may also be used depending on subsystem needs. The key is not just making the part, but making it repeatably, inspectably, and within aerospace tolerances. In your answer, talk about composites, CNC machining, welding, additive manufacturing, casting, bonding, inspection, repeatability, tolerances, and design for manufacturing in aerospace hardware. Question 12. How would you plan a test for a propulsion subsystem? I would begin by defining the objective: performance verification, endurance, leak check, ignition behavior, or qualification. Then I would identify parameters to measure, such as pressure, temperature, thrust, flow rate, vibration, and valve timing. Safety reviews, hazard controls, and abort criteria are essential before testing. During the test, clean data acquisition matters. Afterward, I would compare results with predictions, inspect hardware, document anomalies, and recommend next actions. Be sure to mention test objectives, instrumentation, safety reviews, operating envelope, acceptance criteria, data acquisition, anomaly response, and post-test inspection or analysis. Question 13. A component fails during vibration testing. How would you investigate the root cause? I would first preserve the failed hardware and test data, then verify whether the test setup matched the intended boundary conditions. Next, I would check acceleration levels, frequency response, resonance peaks, fastener torque, material defects, and workmanship issues. I would compare test results with modal analysis or FEA predictions. Root cause may be design, manufacturing, assembly, or test configuration. Corrective action should be specific, documented, and verified through retest. While answering, focus on preserving evidence, reviewing test setup, checking resonance, workmanship, material defects, boundary conditions, FEA correlation, corrective action, and retesting. Question 14. How comfortable are you with engineering drawings, tolerances, and GD&T? I understand that drawings are the contract between design, manufacturing, and quality. I would read the part geometry, datums, critical dimensions, tolerances, surface finish, material, heat treatment, and inspection notes. GD&T helps control functional requirements like flatness, position, perpendicularity, and runout. For aerospace parts, small deviations can affect assembly, sealing, or load paths. I would ask questions early rather than assume, especially on critical interfaces. Make sure to cover drawing interpretation, dimensions, datums, tolerances, surface finish, fits, inspection requirements, manufacturability, and communication with production or quality teams. Question 15. Why are documentation and configuration control important in aerospace engineering? Aerospace hardware must be traceable from design to manufacturing, testing, and flight use. Documentation captures what was built, which revision was used, what material batch went in, and whether inspections passed. Configuration control prevents teams from using outdated drawings or changing hardware informally. If an anomaly occurs, records help identify affected parts quickly. Good documentation may feel slow, but it protects safety, quality, and mission reliability. In your answer, talk about traceability, revisions, test records, material certificates, non-conformance handling, flight safety, audit readiness, and avoiding uncontrolled design changes. Question 16. How would you work in a startup-like aerospace environment with ambiguity and tight timelines? In a fast-moving aerospace company, I would focus on clarity, ownership, and disciplined execution. If a requirement is unclear, I would ask early and document assumptions. I would prioritize tasks based on safety, mission impact, and schedule criticality. Speed is important, but not at the cost of uncontrolled changes or poor testing. As a GET, I would stay flexible, learn from senior engineers, and contribute wherever the program needs support. Be sure to mention prioritization, ownership, communication, quick learning, asking for clarity, balancing speed with safety, and adapting across design, testing, and manufacturing tasks. Question 17. Tell me about a technical project where you solved a real engineering problem. I would choose one project where I personally contributed, not just observed. I would explain the problem, constraints, design choices, and calculations or simulations used. Then I would describe how we built or tested the system and what failed initially. Interviewers value honest troubleshooting more than perfect outcomes. I would end with measurable results, such as weight reduced, efficiency improved, error reduced, or test success achieved after iteration. While answering, use a clear. Question 18. Which engineering tools or software have you used, and how have they helped your work? I have used tools like CAD for modeling, ANSYS or similar software for structural checks, MATLAB or Python for calculations and data analysis, and Excel for quick engineering estimates. I would emphasize that tools support judgment. They do not replace fundamentals. For example, before trusting FEA, I would check boundary conditions, mesh quality, material inputs, and hand calculations. Good engineers know both how to run software and how to question results. Make sure to cover relevant tools like CAD, ANSYS, MATLAB, Python, Simulink, Excel, data analysis, version control, and the engineering judgment behind tool outputs. Question 19. What safety practices would you follow while working around propulsion systems or test facilities? Safety is non-negotiable around propulsion systems because stored energy, pressure, heat, chemicals, and electrical systems can be dangerous. I would follow approved procedures, use PPE, respect exclusion zones, and never bypass interlocks or checklists. Before testing, I would ensure hazards, abort criteria, communication protocols, and emergency actions are clear. If I notice an unsafe condition, I would stop and escalate. A successful test is one that is both technically useful and safe. In your answer, talk about hazard identification, PPE, checklists, pressure systems, propellants, electrical safety, exclusion zones, emergency procedures, and never bypassing test protocols. Question 20. Describe a time you failed or made a mistake. What did you learn from it?
I would pick a real mistake, preferably technical, and take ownership without blaming others.
For example, I might explain that I assumed a boundary condition in analysis and later found the test setup behaved differently. I would show how I identified the root cause, corrected the model, and added a checklist for future work. The message should be maturity. I learn quickly, document lessons, and reduce repeat mistakes. Be sure to mention a genuine technical or teamwork mistake, ownership, root cause, corrective action, learning, and how you changed your process afterward. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.